All right, today for this video, we're going to talk about project evaluation and review technique. I should say not project evaluation, but probabilistic evaluation and review technique, or PERT, P-E-R-T. And that's where we'll be for this video. You'll find it again under the Chapter 9 in your textbook with greater detailed explanations. Again, you've seen this slide a couple of times now. The PERT technique is still going to rely on the process of determining the critical path. The thing that's going to be different for this work that we're going to do today is going to be focused all around, beginning around the duration, because for the critical path method, the duration was fixed and constant. But for PERT, probabilistic evaluation and review technique, as the name implies, the duration is random. And that's probably more realistic assumption, because these tasks, while they may have a forecast time of when they'll be completed, as I mentioned a few videos back, things happen. Deliveries don't come on time. Workers get ill. Things like coronavirus happen. So things change. And so the actual duration of these activities is a random variable and not constant. So this is the process of how to deal with the situations where we have a random variable for our each one of our tasks or activity durations. And so we're going to lean on our previous example again. We're going to continue with our 7-task network. But in this case, the information that we've got about our project is as follows in terms of the actual task completion times. And again, you'll recognize again our tasks 1 through 7. Now we're given 3 pieces of information about each task, about the completion time of each task. And so, for example, for task number 1, if the best thing happens, optimistically, we're optimistic that we can complete. If everything goes as well as possible, we can complete in 10 weeks. Our most likely time, as it was previously, is 12 weeks. But the pessimistic time, if things go poorly, we believe we can complete in 14 weeks. And so task 1 is going to be completed somewhere between 10 weeks to 14 weeks, but we don't know exactly when. 10, 11, 12, 11 and a half, 13 and a half, somewhere in here, it's going to be completed. So now, in order to address that and to be able to get a grasp of how things are going to work, we have to compute using these values. We have to compute the task mean, average. Again, you'll remember the term mean, and it means the same thing as average. It's just another word for average. And we need to calculate the task variance. And then, given this information, we can, using the critical path method, we can then begin to answer the questions like, what's the probability that we can complete this home within 34 weeks? So it's a very powerful tool. And the other thing that I want to point out, we're going to use a variable name, and the variable name for the most optimistic time of completion for each task is A. The variable name for the most likely completion time is going to be M, or the middle time, if you will, median time, and B for the pessimistic completion time. So those are the variable names we're going to use as we go forward with our calculations. And so let's look at how we're going to do this. Now, the book explains this better in greater detail, not in better, but in greater detail. And for each one of these tasks, we're going to use with the beta distribution, properties of the beta distribution. And again, that you need to accept this as fact. Again, if we were in a different class, we would derive these terms, but not too terribly difficult to derive. But we're going to do the following. We're going to compute the task mean completion time and the task variance for each one of these tasks using these terms A, B, and M. Okay, so I'm going to do one example, and then I'll leave it to you to do the others. So let's see how this works for. Let's just pick a task that's on the critical path. Let's pick task 4 as our example. All right, and so what we know from task 4, we know that the term A is going to be 6. We know that M is going to be 12, and we know that B is going to equal to 18. So we're going to use these to calculate. So what's our task mean time? So we're going to substitute these values in for, we're going to substitute 6 in for A plus 4 times our mean value, which is 12, plus 18 for the B value, and we're going to, let me see if I can make this work. Good. We're going to divide that all by 6 to calculate our mean. And if you'll notice in the numerator, that's going to be 6 plus 18 is 24, and 4 times 12 is 48. 24 and 48 is 72, and we're going to divide that by 6. And so our mean completion time, 72 divided by 6, it's going to be 12. Okay, so that's going to be our mean completion time is 12. And our task variance, we're going to calculate this quantity B, which is 18, and we're going to subtract from that A, which is 6, and we're going to square that, and then we're going to divide that. We're going to divide that quantity by 36. And when we do that, if you'll notice in the numerator, that's 12 squared, which is 144 divided by 36. And this turns out to be, let me quickly do that calculation. I can't do that one in my head. That's 144 divided by 36, and that is 4 even. So this is 4.0. And so our task variance for task 4 is 4.0. Should have been able to do that in my head. Okay, so That's just for that one task. Now you'll want to do this for each one of the tasks that's at hand. I will leave that to you for an exercise. I'd encourage you to do it for each one of these, but these are the formulas. I think one of the things that I'll point out here, particularly with respect to this term here, Y4 and Y6. If you'll notice in the numerator, this is actually an average, as you would expect, because we're calculating a mean. But in the numerator, there's, if you will, one part A, 4 parts of the most likely, if you will, one part of the optimistic, 4 parts of the most likely, and 1 part of the pessimistic. So there's 6 parts, if you will. 1, 4, and 1 is 6. And so we're taking those 4 parts of those numbers and dividing that by 6 to get this average. In this case, for task 4, is 12 weeks. So when you complete all of those, and again, it's not hard, I would encourage you to complete those, you're going to get what we have on our next slide. And you can see, again, here's our task mean for task 4, our task variance for task 4. Now, you'll notice, and this is not an accident, you'll notice that each one of our, of course, first of all, I want to point out the same network that we've been using. And the task mean was, if you calculated this out correctly, the task means are the same that we've been using. That's because I want to skip over the critical path method part. But what you would do is, in each case, if for any of these, you would take whatever mean that you get, and you would put it into your duration. And that could be any value. It could have decimals. It doesn't have to be whole numbers. And again, you take 8 and associate it with task 2. You take 6 and associate it with task 3, so on and so forth. And then go through that process of early start, early finish, late start, critical path, and determine how long the task takes. We've already done that work, and we know it's 36 weeks. And then again, here are the respective variances for each task, and we're now going to use that information. So we know that the average time that our process can be completed in is in 36 weeks. But what we want to know is, what's the probability that the project can be completed in 34 weeks rather than 36 weeks? And this is where we're going to use some probability theory that we've talked about previously. So we're going to see how that works on the next slide. I hope you were able to calculate these values and determine that these are all correct. If not, please try. Okay. So on this slide, you'll see I brought forward the information from the previous slide in terms of the task means and the task variances. The first thing that we're going to do is, as you can see here, we will assume, and this, the property, let me back up. We're going to assume that the completion time, the project completion time, has the normal distribution. And the reason that we can assume that relies on the central limit theorem that says the sum of many random variables approaches the sum of the average of many random variables approaches a normal distribution. And so we're going to assume that the central limit theorem holds, which does, and we're going to assume that the completion time has the normal distribution. In fact, let me write that in. So the completion time has as the normal distribution. Okay. We also know from previous work that the average, the mean of that project completion time is 36 weeks. So the mean of this distribution is 36 weeks. And using our diagram, we want to determine the probability that we can complete our housing project in less than 34 weeks. Now, you'll notice if the mean is 36 and the axis here is our completion time, 34 weeks, even though this line is not straight, is less than 36 weeks. And so at some point to the left of our mean is this point 34. So the probability that we can complete in less than 34 weeks is this area that corresponds to the left of and under the curve of left of 34 and under this curve. And we're going to use our properties of our normal distribution to continue to find out this probability. The first step that we're going to do is we're going to determine the project's variance, not the task variance, but the project's variance. And the project variance is based on the sum of the task variances of tasks on the critical path. Okay. And so that's why I have above here, why I have the critical paths highlighted, because we're going to add up the variances of those tasks on the critical path of 0.44, 0.25, 4, and 0.11. And so those variances are, pick a different color, those variances are 0.44 plus 0.25 plus 4 plus 0.11. And when you do this addition, that variance is, it's going to be 4.80, 4.80. And this is the project variance, or sigma squared. All right. So 4.80 is our project's variance, which is the sum of those variances of the critical path. All right. The next thing that we're going to do is we're going to calculate the square root. We're going to calculate the standard deviation, because all we're trying to do, hopefully you'll remember this, what we're trying to do is we're going to try to find the z-value. We're going to try to find the z-value that corresponds to this point 34, where 0.34 is our x value. All right, and so we're working our way down to try to find the z-value. Then, of course, we'll use that z-value over here to determine what that probability is based on the table of the normal distribution. All right, so then the next step is to calculate the standard deviation, and the standard deviation is going to be the square root. We use the Excel term at SQRT, the square root of 4 point, and again, this is going to be 2.19. So we know now our standard deviation, this is the project. That's our project standard deviation. Okay. So now we're going to use that to calculate our z value, and we're going to use, we know again that our x is 34, our mean is 36 from our network, and now we know our project standard deviation, so we can calculate the z value, and this is going to be x is 34 minus 36. Again, it's going to be negative because it's on the left side of our mean, and our standard deviation is 2.19. Once we do this calculation, that's 2 divided by 2.19, excuse me, not 2, it's negative 2 divided by 2.19, and this is going to be equal to 0.91, negative 0.91, which is our z value. Okay. And so now we're ready to use our chart. All right. So here's the issue. Now we've got we want to calculate the probability that z value is less than negative 0.91. Well, we also know that if we went 2 units to the right, change colors. If we went 2 units to the right up here, see if I can get this approximately correct. There we go. And if we went 2 units to the right, we would know that this blue area that's above this area that's above 38 under the curve, because the normal distribution is symmetric, is the same as this red area. And so what we're going to do is we're going to find in our table of normal distribution, I'm going to go show you that in a minute, but what we want to calculate next is we want to calculate the probability that z is, and this should be less than or equal to, but is less than or equal to negative 0.91. Well, that's the same as 1 minus the probability, or that's the same as, let me start it this way, it's the same as the probability that z is greater than positive 0.91. In other words, again, this value is this area here. That's the part that's greater than positive 0.91. All right, and what I also know is that that's the same as 1 minus the probability that z is less than positive 0.91. Go back here and write this. That's going to be equal to. Okay. So let's take a look at this. What this means. This value, I'm going to change colors again. Hopefully the color change helps. This value, I need to get my pencil. This value in green is the same as everything. Actually, it's this value. The green value is everything to the left of, including the red, it's everything to the left of the blue. All right. And so consequently, 1 minus this is the same as this. Now let's go to, so what now we want to find? We want to go to our chart, which is our next slide, and we want to find this value of z. We want to find the value of z that corresponds to positive 0.91. And so let's find that value. Positive, here's 0.9, and here's 1, the value of 1. So we want to see where those two intersect, which is here. Okay. And then we're going to calculate. We know that the value that we want to find is 1 minus this 0.8186, which is equal to 0.1814. So that's 18.4%, that chance of finishing in 34 weeks, finishing the project. PRC, house construction, 4 weeks. And so that's how we use this. We determine that. Now the next slide is going to be, I know that was a little bit quick and a little bit. The next slide summarizes all of that. I encourage you to look at that carefully and make sure that that you understand how that works and how that comes together. Again, don't hesitate to ask if you have questions. Now, before we go on, there's one other thing I want to discuss here quickly. Now, let's suppose, given this our example, that management desires to be complete within complete the project within 34 days. Okay. Management desires to complete the project within 34 days. So our X value is still 34. We'll want to remember that X is still 34. We also want to remember that our standard deviation for the project still is 2.19. So what we're trying to find in this case is we want to find the mean, so that the mean in relation, the mean here in relation to our X value results in a probability of completion of at least 75%. So we're still going to have in our with our normal distribution, the mean is going to be still. Oops, let me erase that and restart. The mean is going to be here still in the middle. That's the mean. Again, let me try that again. That's our mean. Okay. So in order to achieve 75% that'll be completed within 34 days, 34 days has to be, think about this carefully, will have to be somewhere to the right of the mean, because what we want is the probability that we complete in less than 34 days has to be 75%. So we want this value to be 75%, the area under the curve to be 75%. And so in order for that to happen, this mean has to be to the left of 34. So the next step that we want to do is we want to use the information that we know. We want to actually calculate. We want to determine. We want to find the z-value that corresponds to 75%. Okay, so the z-value that corresponds to 75% from the table. That's what's missing. Okay, so let's go to the next slide and see what that corresponds to. All right, so the z-value that corresponds to 75%. So we're looking in the table for the problem for 0.75. And so within the table, let's see, there's 0.73, 0.77, 0.74, 0.7486, 0.7517. So at these two values, we're going to choose, and we're going to choose the larger because we want our chance of completion to be at least 75%. And so that value that corresponds for our z-value is 0.6. We read over here to the left, and then we read up, and then we add 0.6 and 0.08 together. And so what we now know is that our z-value that corresponds to 0.75 is 0.68. All right. So now let's go back and finish this work. So again, we're trying to find the mean, and we know again that that 34 is our x value, and we know that we want 75% to be to the left. And we know that z-value, and so we're working backwards to find the mean. And so what we want to determine is that mean is, we know the z-value is 0.68, and we know that's going to, let me use a different color than red. We know our z-value is 0.68. And we're going to calculate our x minus mu, but the mean now is unknown. So we want to calculate 34 minus the mean and divide that by our standard deviation, 2.19. And we're going to use that to determine, to find the mean. So what we're going to do a little arithmetic. And a little algebra. First of all, I'm going to multiply through. I'm going to find, since 2.19 is, I'm going to multiply through by 2.19 times 0.68. And that's going to be equal to 34 minus the mean. All right. And then the next step is I'm going to subtract 34 from both sides. So on the left side is minus 34 plus 2.19 times 0.68, and that's going to be equal to the negative mean. And then the last step, I'm going to multiply through by a negative, and so this is going to be on the left side 34 minus 2.19 times 0.68. And on the right side now, this is going to be the mean. So now when we calculate these values, we're going to determine what that mean is, and that calculation is, give me just a minute, 2.19 times 0.68 is 1.49 minus 30 or 34 minus 1.49, and that is that's 32.5. So 34 minus 1.49 equals 32.51, and this is our mean. So now, why is this important? Why is this important? Because now that we know that the mean is 32.5. I'm just going to round that to 32.5. So what does that mean in terms of our original problem? We know that the original mean for the project was how many weeks? 36 weeks. And now with this information, in order to complete the project within 32 weeks, to have a 75% chance of completing within 34 weeks, our mean has to be at 32 weeks. And so now we know we have to crash. We would have to crash this network by 3.5 weeks in order to meet that standard. And that's now where we would go back with our crashing process and crash in order to meet that. So that's that example. I'm going to actually work through another example in a minute in another video, and I encourage you to work through this and make sure that you understand that. And again, see me if you have questions. Last slide here is just a summary of all the things that we've done. Again, the information that you're given, how to calculate the mean, how to calculate the variance, complete the completion time with the critical path method, calculate project variance, and then assuming the normal distribution, use the normal distribution to answer the questions that we need to have answered. Okay. All right, again, thank you. I'll go through one other example of PERT for you to use.